What we want to do now is combine skills that we learned in chapters 2, chapter 3, and chapter 10. From chapter 2, we learned how to turn names into chemical formulas and chemical formulas into names. In chapter 3, we learned how to convert grams into moles, how to calculate a molar mass, how to balance a chemical equation, and how to do calculations based on solution stoichiometry. And then from chapter 10, we learned the gas laws. And in this particular problem, we're going to need the ideal gas law. So let's go ahead and get started. Tetraphosphorus trisulfide has the chemical formula. Phosphorus is P. Tetra is the prefix for 4. And sulfur has the symbol S, and trisulfide, we know it's binary because it has an IDE ending. There's 3 of the sulfurs because it has a tri as a prefix. It burns, and if we know that it burns, we know it's a combustion reaction, and if it's a combustion reaction, we know that O2 gas is one of the reactants. When it burns, it forms tetraphosphorus decaoxide. Again, we have P4. Deca is the prefix for 10. Again, it's a binary compound because it has the IDE ending, and it's oxygen because it's an oxide. And it also forms sulfur dioxide gas. And sulfur dioxide has this formula. 1 sulfur, 2 oxygens, the prefix for 2. And so we have a gas. Before we can use this equation to determine the number of moles of sulfur dioxide, which we'll use in the last step of our problem, we need to balance the chemical equation. So let's go ahead and do that. There are no metals in this reaction, so we'll start with phosphorus. We have 4 phosphorus on the reactant side, 4 phosphorus on the product side, so phosphorus is balanced. We have 3 sulfurs on the reactant side, 1 sulfur on the product side, so we need to change the coefficient of sulfur to 3. Now all we have to do is balance the oxygens. Since there's just O2 on the reactant side and there's a multiple of oxygens on the product side, we'll count up the number of oxygens on the product side. We have 10 oxygens plus 3 times 2, that's 6 oxygens. 6 plus 10 is 16, so I just need to change my coefficient of O2 to 8. All right, my chemical equation is balanced. I'm ready to do the reaction stoichiometry, calculate the number of moles of sulfur dioxide, then we can use the ideal gas law. So what I have is 0.800 grams of tetraphosphorus trisulfide. In order to do my solution stoichiometry to solve for the number of moles of sulfur dioxide, I need to convert my 0.800 grams of P4S3 into moles. And the way you convert grams to moles is to divide by the molar mass. So we'll put grams in the denominator, moles in the numerator, and it's 1 mole of 220.06 grams per 1 mole. Then we need to convert moles of P4S3 into moles of sulfur dioxide. So this will be sulfur dioxide in the numerator and tetraphosphorus trisulfide in the denominator. And we look to the coefficients for that mole to mole ratio, and we find that it's a 1 to 3 mole to mole ratio. So grams of tetraphosphorus trisulfide divided by grams of tetraphosphorus trisulfide cancels. Moles of P4S3 cancels moles of P4S3, and we wind up with moles of SO2. And when we do that, we get 0.0109 moles SO2. All right, now that we've got the moles of SO2, we know that we need to use the ideal gas law because it's looking for a volume. They've given us a pressure. We now have a number of moles, and they've given us a temperature. We're going to solve for volume. And if we're solving for volume, we just divide both sides by the pressure, and we wind up with the equation volume in liters is equal to the number of moles times R times the absolute temperature in kelvins divided by the pressure. So we need to go ahead and do a few conversions. The pressure is equal to 725 torr, which we need to convert to atmospheres. And we do that by dividing by 760 torr per atmosphere. And that gives us a grand total of 0.954 atm. That's in atmospheres. Then we need the temperature to be in Kelvin. The temperature is given to us as 32 degrees Celsius, which we'll go ahead and convert to kelvins by adding 273, which gives us 305 kelvins. All right, now we're ready to plug in our values to the formula that we have derived for calculating the volume. And so we'll get the volume of sulfur dioxide gas. Remember, we're going to get it in liters, and we'll have to convert it to milliliters later. So this is the number of moles, 0.0109 moles of sulfur dioxide, times the gas constant, which is 0.0821. That's in liters. Liters times atmospheres divided by moles times kelvins times the absolute temperature, which is 305 kelvins. And that's all going to be divided by the pressure in atmospheres, which is 0.954 atmospheres. We'll go through a quick check. Make sure we've set our problem up correctly by canceling the units. Atmospheres over atmospheres cancel. Moles over moles cancels. The temperature in kelvins over kelvins cancels. And that leaves us with our volume in liters. Once we do the calculations carefully, we wind up with 0.286 liters. And that's our answer in liters, but we were requested to get the volume in milliliters, so that's going to be our 0.286 liters. And we'll go ahead and we'll multiply by 1,000 because there are 1,000 milliliters in every liter, which gives us a grand total of 286 milliliters.